Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today, we are going to discuss about the module Ensemble Theory, Quantum Part 3, Ideal Bose Gas from paper Statistical Mechanics. This module, Ensemble Theory, Quantum Part 3, Ideal Bose Gas, has been developed for postgraduate level as per the following subtopics: degenerate Bose gas, thermodynamic properties of a Bose gas, namely equation of state, number density, internal energy, specific heat, equation of state in Virial expansion, Bose-Einstein condensation, in which we will see conditions for the onset of Bose-Einstein condensation, visualize Bose-Einstein condensation in momentum space, calculate internal energy, specific heat at constant volume of Bose-Einstein condensate, pressure, entropy, isotherms for an ideal Bose gas, and adiabatic relations of an ideal Bose gas. We will also see how Bose-Einstein condensation can be experimentally realized in the case of liquid helium and ultra cold atomic gases. So students, let us see what are we going to learn in this module. Understand the difference between an ideal classical gas and an ideal Bose gas arising because of indistinguishability of particles leading to quantum effects not observed classically. See that there are two kinds of Bose gases with zero mass and zero chemical potential, and the other with non-zero mass and chemical potential less than zero. We will understand in this module that the relevance of mean thermal wavelength or thermal de Broglie wavelength is a deciding parameter to characterize when are the quantum effects significant. Understand how the behavior of a Bose gas is different from an ideal classical gas. Understand when is Bose gas said to be degenerate. Calculate thermodynamical properties with equation of state, number density, internal energy, specific heat, Helmholtz free energy, and entropy of a Bose gas at T not equal to 0 involving the so-called Bose integrals. Learn that the non-degenerate Bose gas for which n lambda cube upon V multiplied by curly G is very much less than 1 behaves like a classical ideal gas. We will also understand through virial expansion of the pressure that an ideal Bose gas, despite the absence of any interaction gas, shows an inherent attractive behavior because of symmetric nature of the multi-particle wave function involved. Learn that as T approaches infinity, pressure and specific heat approach classical values. Learn that specific heat at constant volume versus T curve has a maximum at T is equal to Tc, where derivative of specific heat at constant volume is discontinuous. Learn how with decreasing temperature, chemical potential starts increasing and vanishes at a temperature Tc called Bose-Einstein temperature, which gives rise to Bose-Einstein condensation. This phase transition is like superfluid transition in liquid helium and condensation of copper pairs in the BCS theory of superconductivity. We will underline the fact that Bose-Einstein condensation takes place in a non-interacting gas which happens in momentum space and not in coordinate space. Learn in detail the existence of Bose-Einstein condensate in a dilute gas of magnetically confined group of alkali atoms cooled by evaporation below temperatures of the order of 200 nanokelvin. So in this module on ideal Bose gas, we focus our attention on the study of an ideal quantum gas made up of indistinguishable particles with zero or integer spin, the so-called bosons. Following Bose-Einstein distribution, F epsilon is equal to 1 upon e raised to power epsilon minus mu upon kBt minus 1. In nature, we encounter two kinds of Bose gases, ones with chemical potential mu is equal to 0 and others with mu not equal to 0 but always negative. Examples of the first kind of the Bose gas are black body radiation made up of photons, quantized lattice vibrations in a solid called phonons, and quantized spin lattice vibrations called magnons. Taking mu is equal to 0 also implies that the constraint applied for the derivation of Bose-Einstein distribution for conservation of particles constituting the system is no longer applicable, and these particles can be created by the energy of the heat bath and destroyed by absorption in the heat bath, keeping entropy of the heat bath constant. Particles of the gas with mu is equal to 0 are made up of particles with mass m is equal to 0 and are referred to as quasi-particles. Such Bose particles have momentum p is equal to h bar k and energy E is equal to h bar omega k. In the second kind of Bose particles, the number of particles constituting the system are conserved and have mass. Examples of such systems are liquid helium-4 and vapors of alkali metals whose atoms constituting the vapors have been cooled down to temperature of the order of microkelvin. At epsilon is equal to mu, Bose-Einstein distribution diverges unless mu is negative. In an ideal Bose gas, it is assumed that interparticle interaction is negligible and the quantum effects determine the thermodynamic properties of the system. Second kind of Bose gas also shows a phase transition called Bose-Einstein condensation. Degenerate Bose gas. The name degenerate has a special significance here. A system of bosons, say photons, is said to be degenerate if the average de Broglie wavelength is comparable to or much larger than the average particle distance, such that their wave functions overlap, and that this overlap cannot be ignored and the system can no longer be treated as classical and must be treated quantum mechanically. It is expected that systems at low T, that is high value of beta, will be degenerate. The parameter n lambda cube, where n is the mean number density and lambda is equal to h upon 2 pi m kBt raised to power half, the so-called thermal de Broglie wavelength, becomes a very important criteria as to when will quantum effects manifest. For n lambda cube very much less than 1, system behaves like a classical gas. However, as n lambda cube approaches 1, there is a significant departure from classical behavior and system obeys Bose-Einstein statistics. Even when gas is ideal, the inherent interactions manifest itself in the form of system having symmetric wave function. We will look at first a few thermodynamic properties of Bose gas in detail. Let's look at equation of state. We had derived the equation of state of an ideal Bose gas in earlier module given below. PV upon kBt is equal to minus summation over k log of 1 minus e raised to power minus beta epsilon k minus mu, where beta is equal to 1 upon kBt, mu is chemical potential, and epsilon k is equal to h bar square k square upon 2m. Replacing e raised to power beta mu by z and replacing summation over integration, equation of state can be obtained as PV upon kBt is equal to minus V upon 2 pi whole cube integral from 0 to infinity log of 1 minus z e raised to power minus beta epsilon d cube k. However, here if epsilon and mu simultaneously become 0, the integrand will diverge at the lower limit. To overcome this difficulty, the right procedure shall be to separate out epsilon is equal to 0 term and express 3 as PV upon kBt is equal to minus log of 1 minus z minus V upon 2 pi whole cube integral of log of 1 minus z e raised to power minus beta epsilon d cube k, or PV upon kBt is equal to minus log of 1 minus z minus 4 pi v upon 2 pi whole cube integral from 0 to infinity of log of 1 minus z e raised to power minus beta epsilon k square dk. Noting that epsilon is equal to h bar square k square upon 2m, k square dk is equal to 1 upon 2m upon h bar square raised to power 3 by 2 epsilon raised to power half d epsilon, and we can write equation 5 as pv upon kbt is equal to minus log of 1 minus z minus v 4 pi upon 2 multiplied by 2 pi whole cube integral from 0 to infinity log of 1 minus z e raised to power minus beta epsilon into 2m upon h bar square raised to power 3 by 2 into epsilon raised to power half d epsilon. Putting beta epsilon is equal to x, equation 6 can be written as p upon kbt is equal to minus log of 1 minus z upon v minus 2 pi m kbt upon h square raised to power 3 by 2 4 upon pi raised to power half integral from 0 to infinity log of 1 minus z e raised to power minus x raised to power half dx, or p upon kbt is equal to minus log of 1 minus z upon v minus 1 upon lambda cube 4 upon pi raised to power half integral from 0 to infinity log of 1 minus z e raised to power minus x raised to power half dx, where 1 upon lambda cube is equal to 2 pi m kbt upon h square raised to power 3 by 2, and lambda is equal to h upon 2 pi m kbt raised to power half is thermal de Broglie wavelength. Let us see how integral I is equal to log of 1 minus z e minus x multiplied by x raised to power half dx from 0 to infinity can be evaluated. It can be integrated by parts, as I is equal to log of 1 minus z e raised to power minus x into x raised to power 3 by 2 with limits from 0 to infinity minus 2 upon 3 integral from 0 to infinity z e raised to power minus x upon 1 minus z e raised to power minus x raised to power 3 by 2 dx. Here the first term vanishes, since first term of the product vanishes at upper limit and second term of the limit vanishes at the lower limit. Therefore, equation 9 reduces to I is equal to minus 2 upon 3 integral from 0 to infinity 1 upon z raised to power minus 1 e raised to power x minus 1 x raised to power 3 by 2 dx. Hence, equation 8 can be written as p upon kbt is equal to minus log of 1 minus z upon v plus 1 upon lambda cube into 1 upon pi raised to power half 4 upon 3 integral from 0 to infinity x raised to power 3 by 2 upon z raised to power minus 1 e raised to power x minus 1 dx is equal to minus log of 1 minus z upon v plus 1 upon lambda cube g of the order of 5 by 2 z, where g of the order of 5 by 2 z is equal to 1 upon gamma function of 5 upon 2 integral from 0 to infinity x raised to power 3 by 2 divided by z raised to power minus 1 e raised to power x minus 1 dx, which is a generate integral of the type g of the order nu of function z is equal to 1 upon gamma nu integral from 0 to infinity x raised to power nu minus 1 divided by z raised to power minus 1 e raised to power x minus 1 dx. These integrals are known as Bose integrals, and for small z, this integral can be expanded as a convergent series such that Bose integral g of order nu is equal to z plus z square upon 2 raised to power nu plus z cube upon 3 raised to power nu plus so on. For z very much less than 1, the Bose integral of the order nu becomes equal to z. As z increases, g nu as a function of z also increases monotonically, and over the physical range of interest 0 less than z less than equal to 1 has the maximum value as z approaches 1. For nu greater than 1, then it becomes equal to Riemann zeta function, that is zeta nu. Now let's look at number density. Recall the total number of particles n is equal to summation over epsilon over the average number of particles in each state is equal to summation over epsilon 1 upon z raised to power minus 1 e raised to power beta epsilon minus 1. Summation 14 can be converted into an integral and replacing beta epsilon is equal to x as n is equal to v upon lambda cube into 4 upon pi raised to power half integral from 0 to infinity 1 upon z raised to power minus 1 e raised to power x minus 1 x raised to power half dx. However, here if epsilon and mu simultaneously become 0, the integrand will diverge at the lower limit. To overcome this difficulty, once again, the right procedure shall be to separate out epsilon is equal to 0 term and express 15 as n upon v is equal to 1 upon v multiplied by z upon 1 minus z plus 1 upon lambda cube multiplied by 4 upon pi raised to power half integral from 0 to infinity of 1 upon z raised to power minus 1 e raised to power x minus 1 multiplied by x raised to power half over x. In 16, first term represents number of particles at epsilon is equal to 0 state or p is equal to 0 state and can be written as n0. Therefore, 16 can be written as n minus n0 upon v is equal to 1 upon lambda cube multiplied by 4 upon pi raised to power half integral from 0 to infinity into 1 upon z raised to power minus 1 e raised to power x minus 1 multiplied by x raised to power half dx is equal to 1 upon lambda cube multiplied by Bose integral of the order 3 by 2. Let us have a look at equations 11 and 16 and note some interesting features. For z very much less than 1, a situation close to classical limit, the term log of 1 minus z upon v in equation 11 and z upon 1 minus z v in equation 16 are of the order of 1 upon v and hence negligible. But when z increases and approaches 1, z upon 1 minus z into v is equal to n0 upon v. The number density of particles in zero momentum state is no longer negligible and can be an appreciable fraction of total number of particles n upon v. Such a situation in which an appreciable fraction of particles accumulate in zero momentum state leads to what is known as the famous Bose-Einstein condensation. However, it must be noted that this is not a condensation in the sense of condensation of a gas to a liquid in real space. It is a condensation in the momentum space. Nevertheless, in equation 11, log of 1 minus z upon v remains negligible as z approaches 1 and this term can be altogether neglected. Now let us look at internal energy. The internal energy of the system is given by U is equal to partial derivative of PV upon kBT with respect to beta at constant Z and V, which is equal to kB T raised to power 2 partial derivative of PV upon kBT with respect to T at constant Z and V, or U is equal to kB T raised to power 2 partial derivative of V upon lambda cube multiplied by Bose integral of the order of 5 by 2 with respect to absolute temperature T at constant Z and V, which is equal to V kB T square Bose integral of the order of 5 by 2 multiplied by partial derivative of 1 upon lambda cube with respect to absolute temperature, which is equal to V kB T raised to power 2 G upon 5 by 2 partial derivative of 2 pi m kB T upon h square raised to power 3 by 2 with respect to absolute temperature T, which is equal to 3 by 2 V kB multiplied by 2 pi m kB T upon h square raised to power 3 by 2 into T multiplied by Bose integral of the order of 5 by 2 is equal to 3 by 2 V kB into 1 upon lambda cube multiplied by temperature multiplied by Bose integral of the order of 5 by 2, or U is equal to 3 by 2 kB into 1 upon lambda cube into T multiplied by Bose integral of the order of 5 by 2 into V is equal to 3 by 2 into V into P, or P is equal to 2 by 3 into U upon V. Let us now look at the equation of state in virial expansion. For small values of Z in equation 11 and 16, first term on the right hand side of each of the equations can be neglected, and by noting that n upon V is equal to 1 upon lambda cube multiplied by Bose integral of the order of 3 by 2 is equal to 1 upon lambda cube multiplied by Z plus Z square upon 2 raised to power 3 by 2 plus Z cube upon 3 raised to power 3 by 2 and so on is equal to 1 upon lambda cube summation over L is equal to 1 to infinity Z raised to power L divided by L raised to power 3 by 2, and P upon kBt is equal to 1 upon lambda cube multiplied by Bose integral of the order of 5 by 2 is equal to 1 upon lambda cube into Z plus Z square divided by 2 raised to power 5 by 2 plus Z cube divided by 3 raised to power 5 by 2 and so on is equal to 1 upon lambda cube sum over L is equal to 1 to infinity Z raised to power L divided by L raised to power 5 by 2. By the process of reverting the series, equation of state in virial expansion can be written. The steps involved are writing Z as power series in n upon V, substituting it in equation 22, and finally, by equating like powers of n upon V on both sides, one can obtain coefficients of the power series written in step 1. The value of Z thus obtained in equation 23, one can obtain equation of state in the virial expansion form. So let us perform step 1. Z is equal to A0 plus A1 multiplied by n plus A2 multiplied by n square plus so on, where n is equal to capital N upon V. Step 2. N is equal to 1 upon lambda cube multiplied by A0 plus A1 into n plus A2 into n square plus so on, plus A0 plus A1 into n plus A2 into n square raised to power 2 divided by 2 raised to power 3 by 2, plus A0 plus A1 into n plus A2 into n square plus so on raised to power 3 divided by 3 raised to power 3 by 2 plus so on. On comparing the coefficients on both the sides, we get A0 is equal to 0, A1 plus 2 A0 A1 divided by 2 raised to power 3 by 2 multiplied by 1 upon lambda cube is equal to 1. Therefore, A1 is equal to lambda raised to power 3. A2 plus A1 square divided by 2 raised to power 3 by 2 multiplied by 1 upon lambda cube is equal to 0. Therefore, A2 is equal to minus A1 square divided by 2 raised to power 3 by 2 is equal to minus lambda raised to power 6 divided by 2 raised to power 3 by 2. A3 plus 2 A1 into A2 divided by 2 raised to power 3 by 2 plus A1 raised to power 3 divided by 3 raised to power 3 by 2 is equal to 0. Therefore, A3 is equal to lambda raised to power 9 divided by 2 raised to power 2 minus lambda raised to power 9 divided by 3 raised to power 3 by 2 is equal to lambda raised to power 9 multiplied by 1 upon 4 minus 1 upon 3 raised to power 3 by 2. Thus, Z is equal to lambda raised to power 3n minus lambda raised to power 6 divided by 2 raised to power 3 by 2 n square plus lambda raised to power n multiplied by 1 by 4 minus 1 upon 3 raised to power 3 by 2 into n cube and so on. Substituting Z in equation 23 gives P upon kBt is equal to 1 upon lambda cube multiplied by Z plus Z raised to power 2 divided by 2 raised to power 5 by 2 plus Z cube divided by 3 raised to power 5 by 2 and so on is equal to 1 upon lambda cube multiplied by n lambda cube minus lambda raised to power 6 divided by 2 raised to power 5 by 2 n square plus lambda raised to power 9 multiplied by 1 upon 4 minus 1 upon 3 raised to power 3 by 2 minus 1 upon 8 plus 1 upon 3 raised to power 5 by 2 n cube plus so on. Or P upon kBt is equal to n multiplied by 1 minus lambda cube upon 2 raised to power 5 by 2 multiplied by n plus lambda raised to power 6 multiplied by 1 upon 8 minus 2 upon 3 raised to power 5 by 2 multiplied by n square plus so on. Therefore, PV upon NKBT is equal to 1 minus lambda raised to power 3 upon 2 raised to power 5 by 2 n plus lambda raised to power 6 into 1 upon 8 minus 2 upon 3 raised to power 5 by 2 multiplied by n square plus so on is equal to A naught plus A1 n lambda cube plus A2 n raised to power 2 lambda raised to power 6 plus so on, which can be written as sum over L is equal to 0 to infinity AL multiplied by n lambda cube raised to power L. Equation 27 is the virial expansion of the pressure, which is generally written in the form P upon KBT is equal to n plus B2 as a function of T n square plus B3 as a function of T multiplied by n cube plus so on. BJT in the above relation are called virial coefficients, and these reflect departure from ideal behavior because of some kind of interaction, which is not intermolecular in the present case, this must be emphasized, but arises because of the symmetric nature of the multi-particle wave function of the Bose particles. Note that the second virial coefficient in this case is negative, implying that there is an attractive interaction between the Bose particles. This is not so in the case of fermions. As T approaches infinity, lambda approaches 0, and hence pressure of the Bose gas approaches classic result, that is PV is equal to n Boltzmann constant multiplied by T. Let us now look at the specific heat of such a system. Using formula for internal energy given in equation 21, specific heat at constant volume is equal to partial derivative of internal energy U with respect to temperature, which is equal to partial derivative of 3 by 2 P into V with respect to temperature, which is equal to 3 by 2 N kV partial derivative of PV upon N kV with respect to temperature, or CV upon N kV is equal to 3 by 2 partial derivative of PV upon N kV with respect to temperature is equal to 3 by 2 partial derivative of summation over L is equal to 0 to infinity AL n lambda cube raised to power L multiplied by temperature with respect to temperature is equal to 3 by 2 summation over L is equal to 0 to infinity 1 minus 3L upon 2 multiplied by AL n lambda raised to power 3L, or specific heat at constant volume divided by n kb is equal to 3 by 2 multiplied by A0 plus minus 1 by 2 multiplied by A1 multiplied by n multiplied by lambda cube plus minus 2 multiplied by A2 into n lambda cube raised to power 2. Specific heat at constant volume divided by n kV is equal to 3 by 2 multiplied by A naught plus minus 1 upon 2 multiplied by A1 multiplied by n multiplied by lambda raised to power 3 plus minus 2 multiplied by A2 multiplied by n lambda cube raised to power 2 plus so on, or is equal to 3 by 2 multiplied by 1 plus minus 1 upon 2 multiplied by minus 1 upon 2 raised to power 5 by 2 n lambda cube plus minus 2 multiplied by 1 by 8 minus 2 upon 3 raised to power 5 by 2 multiplied by n raised to power lambda 3 raised to power 2 plus so on, where we have substituted the values of A0, A1 and A2, or specific heat at constant volume divided by n kb is equal to 3 by 2 multiplied by 1 plus 0.0884 n lambda cube plus 0.0066 multiplied by n lambda cube raised to power 2 plus so on. One can note that as T approaches infinity, lambda approaches 0, and hence specific heat of the Bose gas approaches the classical value equal to 3 by 2 n kb. At finite temperature, specific heat of the gas is greater than the classical value. This implies that the specific heat at constant volume versus T graph has negative slope. However, since specific heat at constant volume Cv must go to 0 as T approaches 0, thus Cv versus T graph must have a maxima. This happens at a critical temperature Tc, where derivative of specific heat is discontinuous. Now we will focus our attention on Bose-Einstein condensation. Equation 23 and 33 work well when n multiplied by lambda raised to power 3 is such that temperature is high and lambda, the thermal de Broglie wavelength, which varies as T raised to power minus 3 by 2, remains small. However, as temperature falls, we have to go back to equation 11, 17 and 20. Equation 17 can then be written as Ne upon V is equal to N minus N0 upon V is equal to 1 upon lambda raised to power 3 multiplied by Bose integral G of the order of 3 by 2 is equal to 2 pi m kBT raised to power 3 by 2 divided by h cube multiplied by Bose integral of the order of 3 by 2, where Ne is the number of particles in the excited state and N0 is the number of particles in the ground state, that is, the state with epsilon is equal to 0. For the range of physical interest, that is 0 less than z less than equal to 1, upper bound occurs when z is equal to 1, at which Bose integral of the order 3 by 2 is equal to 1 plus half plus 1 by 3 plus so on, which is nothing but a Riemann zeta function of 3 by 2, which is approximately equal to 2.612. Therefore, Ne, the total number of particles in all the excited states together, has also an upper bound, such that for a given V and T, Ne has to be less than equal to V multiplied by 2 pi m kBT raised to power 3 by 2 divided by h cube multiplied by Riemann zeta function of 3 by 2. There are two possibilities now. If actual number of particles in the system is less than this upper bound, then all the particles get distributed in the excited states and exact value of Z, that is fugacity or chemical potential, gets determined by taking Ne is approximately equal to n. However, if actual number of particles is greater than this limiting value, so the number of particles in excess of this value cannot be distributed in the excited states and must get accommodated in the ground state, which has no upper bound and can accommodate an unlimited number of particles, such that n naught is equal to n minus V multiplied by 2 pi m kBT raised to power 3 by 2 upon h cube multiplied by Riemann zeta function of 3 by 2. And the value of Z can then be obtained using the formula Z upon 1 minus Z into V is equal to N naught upon V. That is, Z is equal to N naught upon N naught plus 1, which is approximately equal to 1 minus 1 upon N naught, which is 1, implying for a given T, chemical potential mu is equal to 0. This interesting result opens up a possibility of accommodating a large number of particles in the ground state and is called Bose-Einstein condensation. And for a given number of particles n greater than Ne, the system can be seen as a mixture of two phases. One phase made up of particles in the excited states, that is Ne, epsilon naught is equal to 0, is called normal phase, and the other made up of N0, number of particles in the ground state, called condensed phase. Now let us look at the conditions for the onset of Bose-Einstein condensation. It is now obvious that for Bose-Einstein condensation to take place, the condition can be expressed as the number of particles must be very much greater than Ne, which is limited to V multiplied by T raised to power 3 by 2 multiplied by 2 pi m kB raised to power 3 by 2 divided by h cube multiplied by Riemann zeta function of 3 by 2. It can be expressed alternatively if we keep n and v fixed as T less than Tc is equal to h square upon 2 pi m kB multiplied by n upon V multiplied by Riemann zeta function of 3 upon 2 raised to power 2 by 3 is equal to 2 pi upon Riemann zeta function of 3 by 2 raised to power 2 by 3 multiplied by h square n raised to power 2 by 3 divided by m kb is equal to 3.31 multiplied by h bar square n raised to power 2 by 3 divided by m kb, where Tc is the transition temperature which depends on particle density of the system and mass of the particles constituting the system. Fraction of particles in the normal phase Ne upon n and fraction of particles in the condensed phase can be written respectively as Ne upon n is equal to T upon Tc raised to power 3 by 2 and N0 upon n is equal to n minus Ne upon n is equal to 1 minus T upon Tc raised to power 3 by 2. Figure 1 shows the plot of fraction of normal phase and a fraction of condensed phase plotted against T upon Tc. It is observed that for T greater than Tc, there is a no condensed phase as N0 upon n approaches 0. Now the question comes, how do we visualize Bose-Einstein condensation in momentum space? Equation 16 for number density has been written in energy representation. It can also be written in momentum space as follows. N is equal to z upon 1 minus z plus 4 pi v upon h cube integral from 0 to infinity of 1 upon e raised to power beta p square upon 2m minus 1 p square dp. Below the transition temperature Tc, as T approaches 0, the integral in the second term vanishes and the first term gives the number of bosons in the state P is equal to 0. So the distribution of particles can be written as dN upon dP is equal to z upon 1 minus z 2 times the Dirac delta function of P plus 4 pi v upon h cube multiplied by p square upon e raised to power beta p square upon 2m minus 1. Noting that twice the integral from 0 to infinity of Dirac delta function delta p over dp is equal to 1. On plotting the particle distribution of Bose particles in momentum space for an ideal Bose gas below the transition temperature, one can visualize the fraction of particles in zero momentum space as shown in figure 2. Now let us calculate internal energy. Recall from equation 20 that internal energy U is equal to 3 by 2 multiplied by V into Kb multiplied by 1 upon lambda cube multiplied by T multiplied by Bose integral of the order of 5 by 2, and from equation 17 n minus n naught upon V is equal to 1 upon lambda cube multiplied by Bose integral of the order of 3 by 2, or n minus n naught is equal to Ne is equal to V upon lambda cube multiplied by Bose integral of the order of 3 by 2, or V upon lambda cube is equal to Ne upon Bose integral of the order of 3 by 2. Therefore, equation 44 can be written as U is equal to 3 by 2 Kb into T Ne Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2. Here the factor Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 gives the deviation of internal energy from the corresponding classical value. Noting from equation 40 that Ne upon n is equal to T upon Tc raised to power 3 by 2, 48 can be written as U is equal to 3 by 2 n kBT Ne upon n multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 is equal to 3 by 2 n kBT multiplied by T upon Tc raised to power 3 by 2 multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 is equal to 3 upon 2 n kBTc multiplied by T upon Tc raised to power 5 by 2 multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2. For T less than Tc, the fugacity Z is equal to 1. Therefore, equation 49 can be written as U is equal to 3 by 2 n kBTc multiplied by T upon Tc raised to power 5 by 2 multiplied by G, that is the Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 is equal to 3 by 2 n kb Tc multiplied by T upon Tc raised to power 5 by 2 multiplied by Riemann zeta function of the order of 5 by 2 divided by Riemann zeta function of the order of 3 by 2. Using the value of Riemann zeta function, we can write U is equal to 3 by 2 n kb Tc multiplied by T upon Tc raised to power 5 by 2 into 1.341 divided by 2.612 is equal to 3 by 2 n kb Tc multiplied by T upon Tc raised to power 5 by 2 multiplied by 0.51 is equal to 0.76 multiplied by n kb Tc multiplied by T upon Tc raised to power 5 by 2. In this region, internal energy U is proportional to T raised to power 5 by 2. At T is equal to Tc, the energy is approximately half that of an ordinary gas at the same temperature. For T greater than Tc, Z is less than 1 and all particles are in excited states, that is N is equal to Ne, or U is equal to 3 by 2 n kBT multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2. For Z less than 1, Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 is less than 1, and therefore in this region internal energy is always less than the classical value of 3 by 2 n kBT. Now let us look at specific heat at constant volume of Bose-Einstein condensate. Specific heat at constant volume is given by Cv is equal to partial derivative of internal energy U with respect to temperature at constant volume. For T less than equal to Tc, it gives using equation 51, or Cv is equal to delta U with respect to T at constant volume is equal to 5 by 2 multiplied by 0.76 multiplied by n kV multiplied by T upon Tc raised to power 3 by 2 is equal to 1.9 n kB multiplied by T upon Tc raised to power 3 by 2. Therefore, Cv is proportional to T raised to power 3 by 2. At T is equal to Tc, we have Cv is equal to 1.9 n kV. This value is much higher than the classical value of 3 by 2 n kB. At T greater than Tc, differentiating 52, we get the specific heat at constant volume is equal to 3 by 2 times n kB multiplied by partial derivative of T multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 with respect to temperature. This differentiation requires knowledge of temperature derivative of Z. From 47, it is clear that Bose integral of the order of 3 by 2 is proportional to T raised to power minus 3 by 2. Therefore, partial derivative of the Bose integral of 3 by 2 with respect to temperature is equal to minus 3 by 2 T multiplied by Bose integral of the order of 3 by 2. And recalling the recurrence relation, Z into partial derivative of Bose integral of the order of nu with respect to Z is equal to Bose integral of the order of nu minus 1. We have Z into partial derivative of Bose integral of the order of 3 by 2 with respect to Z is equal to Bose integral of the order of half. Using 58 and 59, we get 1 upon Z multiplied by partial derivative of Z with respect to T at constant V and N is equal to minus 3 upon 2T multiplied by Bose integral of the order of 3 by 2 divided by Bose integral of the order of half. Carrying out temperature derivative in equation 57, we have specific heat at constant volume is equal to 3 by 2 n kB multiplied by G of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 plus T multiplied by Bose integral of the order of 3 by 2 multiplied by Bose integral of the order of 5 by 2 minus Bose integral of the order of 5 by 2 into Bose integral of the order of 3 by 2. Note, the second terms in this are derivatives with respect to z and are represented by dash, divided by Bose integral of the order of 3 by 2 square multiplied by partial derivative of z with respect to temperature, or Cv is equal to 3 by 2 multiplied by n kb into Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 plus T multiplied by Bose integral of the order of 3 by 2 multiplied by Bose integral of the order of 3 by 2 minus Bose integral of the order of 5 by 2 multiplied by Bose integral of the order of half divided by Bose integral of the order of 3 by 2 square multiplied by z into partial derivative of z with respect to t, or specific heat at constant volume V is equal to 3 by 2 n kV multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 plus T into Bose integral of the order of 3 by 2 into Bose integral of the order of 3 by 2 minus Bose integral of the order of 5 by 2 into Bose integral order of half divided by Bose integral of the order of 3 by 2 square multiplied by minus of 3 upon 2t multiplied by Bose integral of the order of 3 by 2 divided by Bose integral of the order of half, or Cv is equal to 3 by 2 n kV multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 minus 3 upon 2 multiplied by Bose integral of the order of 3 by 2 divided by Bose integral of the order of half minus Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2, or specific heat at constant volume becomes equal to n upon kb multiplied by 15 upon 4 Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 minus 9 upon 4 multiplied by Bose integral of the order of 3 by 2 divided by Bose integral of the order of half. Here we note that term in the parenthesis on the right hand side decreases till in the limit z approaching 0, Cv is equal to n kV multiplied by 15 upon 4 minus 9 upon 4, which is equal to 3 by 2 times n kV. For t is equal to Tc, that is in the limit z approaching 1, Bose integral of the order of half diverges and the second term vanishes, and the contribution comes only from first term, which is the specific heat of constant volume equal to n kV multiplied by 15 upon 4 multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2, both evaluated at z is equal to 1, which is equal to n kB multiplied by 15 upon 4 multiplied by Riemann zeta function of the order of 5 by 2 and Riemann zeta function at 3 by 2, which is equal to 1.925 n kV. It is the same result as given by equation 56. Here we note that term in the parenthesis on the right hand side decreases till in the limit z approaching 0, Cv is equal to n kV multiplied by 15 upon 4 minus 9 upon 4, which is equal to 3 by 2 times n kV. For t is equal to Tc, that is in the limit z approaching 1, Bose integral of the order of half diverges and the second term vanishes, and the contribution comes only from first term, which is the specific heat of constant volume equal to n kV multiplied by 15 upon 4 multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2, both evaluated at z is equal to 1, which is equal to n kB multiplied by 15 upon 4 multiplied by Riemann zeta function of the order of 5 by 2 and Riemann zeta function at 3 by 2, which is equal to 1.925 n kV. It is the same result as given by equation 56. Figure 3 here gives a plot of specific heat of an ideal Bose gas against reduced temperature T upon Tc. It is a continuous curve at T is equal to Tc. However, its slope is discontinuous. Furthermore, since below Tc and above Tc the properties of the ideal gas are different, it may be concluded that there is a phase transition. There is a real system corresponding to helium-4, a bosonic system to which the results of specific heat resemble, though that system is far from an ideal Bose gas behavior. The transition point there is called Lambda Transition, since the specific heat curve of this helium-4 bosonic system resembles the Greek letter lambda. Now let's look at the pressure. From equation 20 we know that PV is equal to 2 upon 3 U is equal to V kBT upon lambda cube multiplied by Bose integral of the order of 5 by 2. For T less than Tc, Z is equal to 1 and Bose integral of the order of 5 by 2 is equal to 1.341, and therefore in this region we see that pressure is independent of V, implying pressure is proportional to T raised to power 5 by 2. Figure 4, which is PT diagram of the ideal Bose gas, shows Pt raised to power 5 by 2 is equal to constant curve. Condensed phase lies on the line and below it is the normal gas phase. At T is equal to Tc, P is equal to 1.341 multiplied by 2 pi m raised to power 3 by 2 h cube multiplied by kBTc raised to power 5 by 2. Using 39, where kBTc is equal to h square upon 2 pi m multiplied by n upon v Riemann zeta integral at 3 upon 2 raised to power 2 by 3, we get in 69 P is equal to 1.341 divided by Riemann zeta function at 3 upon 2 into n upon v kVTc is equal to 1 upon 1.341 divided by 2.612 into n upon v kVTc is equal to 0.5133 multiplied by n upon v kVTc, or PV upon n kV into 1 upon Tc is equal to 0.5133. It shows that pressure exerted by an ideal gas at T is equal to Tc is half the pressure exerted by a classical ideal gas. For T greater than Tc, P is equal to kBT upon lambda cube multiplied by Bose integral of the order of 5 by 2 is equal to kBT multiplied by Bose integral of the order of 5 by 2 divided by V upon n into Bose integral of the order of 3 by 2, or P is equal to n kBT upon V multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2. Since the ratio of these two functions is always less than unity, pressure is once again less than the classical ideal gas as T approaches infinity and Z approaches 0, and pressure asymptotically approaches classical value. Now we will have a look at entropy of such a system. For T less than equal to Tc, using 55, the expression for Cv, we can calculate entropy by integrating, that is, S is equal to integral from 0 to T specific heat at constant volume divided by T dt is equal to 2 upon 3 1.9 kb n multiplied by T upon Tc raised to power 3 by 2 is equal to 1.28 Boltzmann constant kb into Ne, where we have used Ne is equal to n times T upon Tc raised to power 3 by 2. In this region, normal phase and condensed phase both are present, but it is the particles any in the normal phase which contribute to the entropy of the system. Contribution to entropy by the particles N0 in condensed phase is 0. At 0 degrees Kelvin, all particles are in the ground state and entropy of the system S is equal to 0. Also recalling the thermodynamical relation gives free energy is equal to internal energy minus T into entropy plus pressure into volume is equal to mu into N, or S upon kBn is equal to U plus PV upon kBTn minus mu upon kBt, and noting that for T less than Tc mu is equal to 0, therefore S upon kBn is equal to U plus PV upon kBTn is equal to 5 upon 3 U upon kBTn is equal to 5 upon T 2 PV upon kBTn is equal to 5 upon 2 V upon n lambda cube Riemann zeta function at 5 by 2 is equal to 5 by 2 Riemann zeta function at 5 by 2 divided by Riemann zeta function at 3 by 2. Since n is equal to ne, S is equal to kBne multiplied by 5 by 2 into Riemann zeta function of 5 by 2 divided by Riemann zeta function of 3 by 2, or entropy is proportional to Ne. For T greater than Tc, S upon kBn is equal to U plus PV upon kBTn minus mu upon kBt is equal to 5 upon 2 PV upon kBTn minus log of z is equal to 5 by 2 multiplied by Bose integral of the order of 5 by 2 divided by Bose integral of the order of 3 by 2 minus log of z. It will be interesting to look at isotherms for an ideal Bose gas. We now consider isotherms of an ideal Bose gas. According to equation 28, at constant temperature, pressure P varies as 1 upon V plus terms of the order of V square for V greater than Vc, while for V less than Vc, it is independent of V. The isotherms are plotted in figure 5 below. This figure shows a PV diagram where dashed line, that is P proportional to 1 upon V raised to power 5 by 3 is the transition line, and the region to the left of this line is condensation region. For Vc1 and Vc2 are the volumes where the isotherms for T1 and T2 touch the transition line. For V less than Vc, pressure remains constant, whereas for V greater than Vc, as volume decreases, pressure increases, till the isotherm touches the transition line. The region below transition line is a coexistence region having both the condensed phase and the normal phase. As the volume decreases, the number of particles in the condensed phase increases. It can also be seen from the isotherms that pressure in the coexistence region is determined by the temperature alone. For T greater than T1, P2 is greater than P1. Also in the coexistence region, since pressure is solely dependent on temperature, it corresponds to first order phase transition. Now we look at the adiabatic relations of the ideal Bose gas. For a reversible adiabatic process, entropy is constant. Therefore, from equation 75 for T less than Tc, S is equal to 1.28 kb multiplied by Ne, where Ne is a constant. From equation 47, V upon lambda cube is equal to Ne divided by Bose integral of the order of 3 by 2. We have V upon lambda cube is equal to Ne divided by Riemann zeta function of the order 3 by 2 at 1, which is equal to a constant, and hence V upon T raised to power minus 3 by 2 is equal to a constant. On the other hand, for T greater than Tc, from equation 80, it follows that fugacity Z and Bose integral of the order of 5 by 2 are both constant. Hence, from equation 73, P upon T raised to power 5 by 2 is equal to constant. Eliminating T from 82 and 83, we get adiabatic equation of an ideal Bose gas, which is PV raised to power 5 by 3 is equal to constant. Now, it will be interesting to look at and see how Bose-Einstein condensation was experimentally realized. Let us note that in the study of ideal Bose gas model, it is natural to look for its manifestation in nature in the form of Bose-Einstein condensation. The real challenge in observing this lies in getting a gas of non-interacting bosons. This requires average particle-particle distances Rd of the boson gas to be greater than the range of particle-particle interaction, which we are representing as Ri. Typical range of particle-particle interaction is of the order of S wave scattering length, that is As. Also, the thermal de Broglie wavelength lambda should be much greater than the particle-particle distance Rd. So, when we are able to satisfy the criteria, lambda is very much greater than Rd, is very much greater than Ri, which is approximately equal to the S-wave scattering length, we can treat the bosonic system as an ideal Bose gas. Its first signature was thought to be not in the so-called non-interacting gas but in a quantum liquid in the form of liquid helium-4, which is a collection of bosons and has an extraordinary property of superfluidity, which was to begin with thought to be attributed to Bose-Einstein condensation. It was only lately in 1995 that Bose-Einstein condensation was demonstrated in the dilute gas of rubidium-87 atoms when its vapors were cooled below 170 nanokelvin. We will look at these two experimental realizations of Bose-Einstein condensation in what follows. Let's have a look at liquid helium-4. Helium is a very interesting element which has two isotopes, helium-4 and helium-3. Helium-4 is most abundant and helium-3 the least abundant. Helium was found to be in a liquid form only at extremely low temperatures at 4 degrees Kelvin or below. Helium-4 atoms are having even number of spin half particles and are bosons, and helium-3 atoms having odd number of particles are fermions. Liquid helium-4 has an interesting phase transition called Lambda transition from phase called helium-1 to a phase called helium-2 as shown in figure 6. The later phase is a superfluid phase. This transition takes place at T lambda is equal to 2.18 K. Interestingly, if we take the mass of helium-4 atom to be m is equal to 6.65 into 10 to the power minus 4 gram and use the formula for calculating the transition temperature with specific heat, specific volume V lambda, and Bose integral of the order of 3 by 2 evaluated at 1 is equal to 2.612, one gets Tc is equal to 3.12. This number is very close to T lambda, but if we look at the experimental CVT curve for helium-4 as shown in figure 7, it has a logarithmic divergence and is a departure from finite specific heat at constant volume at Tc in an ideal Bose gas, which we discussed earlier. And therefore, this transition needs to be looked at and into by including rather strong interaction among helium-4 atoms. This has been a question which was pondered over by Landau and Feynman particularly in the context of superfluidity shown by helium-4. We will look at this system in more details in the next module. So, one of the most essential things which one needed to do was to have what we call ultra-cold atomic gases. Bose-Einstein condensation in the ultra-cold atomic gases of rubidium-87 isotope by Carl Wieman's group in Colorado was the first demonstration of a pure Bose-Einstein condensate in matter in 1995. In quick succession, Ketterle's group in MIT, Massachusetts demonstrated Bose-Einstein condensation of sodium-23. This was made possible by convergence of many innovative technologies to magnetically trap a group of thousands of atoms first cooled by counter-propagating laser beams and further cooled by evaporative cooling. Magnetic trapping made sure that a desirable number of bosons are available in a specific volume. Now the question is, how do alkali atoms with valency 1 behave as bosons? Alkali atoms chosen for this purpose have valency 1 leading to half integer spin, that is h bar upon 2. But for the Bose-Einstein condensation, one needs integral spin. Since nuclear spin of alkali atoms, that is of rubidium-87, sodium-23 and lithium-7 is also half integer spin, that is 3 by 2 h bar. So the first requirement which needs to be fulfilled is the coupling of the electronic spin of the electrons with the nuclear spin. This requires total spin J is equal to I plus S in the range of modulus of I plus S and modulus of I minus S, where I and S are respectively nuclear and electronic spins of the atoms. Therefore, total spin of the alkali atoms is either 2H bar or 1H bar. This also requires that isotopes of the alkali atoms chosen should be such that both atomic number and mass number should be odd, so that Z plus A is even and atom as a whole has even number of fermions, so that total J is integer and hence a boson. So it will be interesting to estimate Tc for rubidium 87. By using formula, Tc is equal to 3.31 h bar square n raised to power 2 by 3 divided by m kb. Rubidium 87 has a typical value of density of the order of n approximately equal to 10 raised to power 18 per meter cube. Using m is equal to 37 times mass of proton plus 50 times mass of neutrons plus 37 times mass of electrons, one gets Tc of the order of 18.28 nanokelvins, that is of the order of 10 raised to power minus 7 K. Furthermore, hyperfine interaction energy for rubidium is about 0.3 Kelvin, meaning thereby that below about 0.1 Kelvin, coupling between nuclear spin and electronic spin survives. Thus, at a temperature at about 10 raised to power minus 7 K or below, Bose-Einstein condensation will happen in rubidium 87 and can be experimentally observed. So, many steps to experimentally produce Bose-Einstein condensate were followed. Let us look at the steps to experimentally produce Bose-Einstein condensate. First, pure boson in the form of particular isotopes of say rubidium 87 are taken and put in vacuum. The atoms so taken are cooled to fractions of a degree Kelvin. Then these cooled atoms are put in a magnetic trap, which is pair of coaxial anti-Helmholtz coils with current flowing in opposite direction, leading to a quadrupole field such that in the central region of two coils magnetic field is 0. This region acts as a trap, forming a plus-like configuration with opposite points having same magnetic polarity. A laser with a precisely calculated wavelength tuned slightly below the resonant frequency of the atoms in the trap is beamed on the atoms. Atoms which are stationary are off the resonance and do not absorb an incident photon. On the other hand, moving atoms are Doppler shifted on resonance to the laser beam, which is moving in a direction opposite to the velocity vector of the atom. These atoms absorb photons from that direction and then re-emits in the random directions, causing a net momentum impulse in a direction opposite to the direction of motion. This results in slowing down of the atoms and hence in lowering the temperature. In fact, the experimental setup uses 3 sets of counter-propagating beams oriented along Cartesian axis. This step has limit to cooling because of recoil limit when the atoms acquire a minimum momentum of the order of momentum of the photons of the laser beam. This step cools the atoms to a temperature of the order of 10 raised to power minus 6 Kelvin. The real challenge in this step is to keep the laser tuned to desirable frequency. Further cooling is caused by evaporative cooling, which essentially allows atoms moving faster to escape from the trap, leaving the lowest energy atoms behind. A stage comes when the only atoms left behind are the ground state atoms, and they coalesce into a Bose-Einstein condensate, which behaves like a single superatom. Rubidium atoms, because of highest mass, could go into the ground state at the highest temperature. The next step was to detect the Bose-Einstein condensate. This is achieved by suddenly switching off the trapping forces, allowing the superatom to expand. Colder the atoms, slower is the expansion of the superatom. Using a resonant laser light, an image of this expansion can be captured. The famous picture shown in figure 8 captures the first Bose-Einstein condensate. So, students, let us summarize what we have learnt in this module. We have learnt that in nature there are two kinds of Bose gases. ones with chemical potential mu is equal to 0 and mass m is equal to 0, and the others with mu not equal to 0 but always negative and mass m not equal to 0. The particles constituting Bose gas follows Bose-Einstein distribution. F epsilon is equal to 1 upon e raised to power epsilon minus mu upon kBt minus 1. We learnt that quantum effects become pronounced when the interparticle distance between the particles is comparable to their average de Broglie wavelength, and wave functions of different particles overlap and system cannot be treated classically. The gas is then said to be degenerate. This happens when Bose gas has very low temperature or very high density. We also learned how to derive following physical quantities for a degenerate Bose gas, namely equation of state in Virial expansion, number density, internal energy, specific heat, and adiabatic equation of ideal Bose gas. We also learned that ideal Bose gas satisfies the same relationship between pressure and energy density as is satisfied in the case of ideal Fermi gas and classical ideal gas, and that specific heat of an ideal Bose gas against reduced temperature T upon Tc is a continuous curve at T is equal to Tc. However, its slope is discontinuous. We learned that there is an upper bound for the number of particles in the excited state of a Bose gas, namely Ne is less than equal to V multiplied by 2 pi m kBt raised to power 3 by 2 divided by h cube multiplied by Riemann zeta function at 3 upon 2, leading to two possibilities. One, Ne less than equal to n when all the particles get distributed in upper states, and second, n greater than Ne such that excess number of particles cannot be distributed in the excited states and must get accommodated in the ground state, which has no upper bound and can accommodate an unlimited number of particles such that n naught is equal to n minus V multiplied by 2 pi m kBt raised to power 3 by 2 divided by h cube multiplied by Riemann zeta function evaluated at 3 upon 2. We learned that the ground state of a Bose gas with momentum equal to 0 is also called condensed state, that the ideal gas with n greater than Ne has two phases, one made up of particles in the excited states called normal phase and the other made up of particles n0 in the ground state called condensed phase. We learned that for a fixed number of particles in volume, the condition of upper bound can be expressed to calculate transition temperature Tc for the onset of particles going in the ground state, or also referred to as onset of the Bose-Einstein condensation, given by T less than Tc is equal to 3.31 multiplied by h bar square n raised to power 2 by 3 divided by m kb. We learned that the fraction of particles in the normal phase and condensed phase are given by Ne upon n is equal to T upon Tc raised to power 3 by 2 and n naught upon n is equal to 1 minus T upon Tc raised to power 3 by 2 respectively, and that the momentum distribution of particles in ideal gas, which is Bose-like, is dn upon dp is equal to z upon 1 minus z multiplied by 2 Dirac delta function of p plus 4 pi v upon h cube into p square upon e raised to power beta p square upon 2m minus 1. We also learned that situation in which an appreciable fraction of particles accumulate in zero momentum state leads to Bose-Einstein condensation. We learned this is not a condensation in the sense of condensation of a gas of a liquid in real space. It is a condensation in the momentum space. We learned how to calculate various physical properties of Bose gas around Bose-Einstein condensate transition temperature Tc, namely internal energy, specific heat, pressure, entropy. Also, we learnt that ideal Bose gas is isotherms such that at V greater than Vc, P is proportional to 1 upon V, and for V less than Vc, pressure P is constant. We learned that the isotherm PV raised to power 5 by 3 is equal to constant represents the transition line. Below the transition line, there is a coexistence region where both condensed phase and the normal phase coexist. We learned that as volume decreases, number of particles in the condensed phase increases. We also learned that quantum liquid of helium-4 is a bosonic system which shows superfluidity and was considered to be manifestation of Bose-Einstein condensation. That Bose-Einstein condensation has been realized experimentally in ultra-cold gases of alkali metals below about 200 nanokelvin, which involved convergence of many innovative technologies to magnetically trap a group of thousands of atoms, first cooled by counter-propagating laser beams and further cooled by evaporative cooling. Thank you.